Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, excited to dive into this week's topic. Looks like a fascinating one.
Yeah, always interesting to see what's new. This paper about explaining LLM decisions using Shapley values, it's piqued my curiosity, to say the least.
Absolutely. I think it hits on a core challenge we're facing right now. How do we really understand what's going on inside these incredibly complex models?
Right, we've built these amazing tools, but they can sometimes feel like black boxes. We throw a prompt in, get an output, but the path taken there is, well, it's often a mystery.
Exactly. And that mystery, that lack of interpretability, is a real problem, especially if we're thinking about using these models in, critical applications or even just relying on them for research.
And that's where this paper comes in, right? Using Shapley values from game theory to try and break down the contributions of each part of a prompt. It's a really clever approach.
Yeah, I'm particularly interested in how they're using it to identify what they call token noise. The idea that an LM's decision can be heavily influenced by, basically, meaningless stuff like articles or even new line characters. That's pretty wild.
It's more than wild, it's kind of unsettling, that something like a new line character could throw the model off like that. It points to a huge gap between how these models process information and how, well, we asterisk do.
And it really highlights the limitations of just looking at the output. We can't just assume that because an LM appears to mimic human behavior, that it's actually thinking or understanding in a similar way. We have to get down to the nuts and bolts and understand the mechanisms.
Exactly, we are seeing that human-like output is not necessarily indicative of human-like processing. I've seen studies that show LMs can exhibit similar biases to humans, but when you dig deeper, you find the why is completely different. It's like getting the same answer, but via totally separate routes.
Yes, and I think this is a perfect example of why we need approaches beyond just more data. The paper's examples are so revealing. They show the model gets hung up on superficial features rather than understanding the actual core semantics, and that just underscores my skepticism about the current deep learning paradigm.
Well, yes and no. I see what you're saying about needing to go beyond more data, but I think this paper doesn't discount the deep learning approach. It actually just highlights the need for better interpretability asterisk within asterisk that approach. This Shapley value method could be a critical tool for that. We need more methods like this to bridge the gap between deep learning and our understanding of how biological intelligence works. That's where neuroscience could play a role.
I agree. This method isn't about replacing deep learning, it's about making it more robust and reliable. We're not going to get to AGI by blindly throwing data into the model. We need tools like these to understand what's actually being learned. The fact that they can apply it to closed source models, that's huge. It means we can get under the hood of models like GPT and Gemini, which were, up to now, pretty opaque.
Okay, yes, I concede that's a strong point. It being model agnostic is very powerful. But still, I remain skeptical about relying so heavily on token-based interpretations. This still just feels like a high-level workaround when what we really need is a fundamental shift in algorithms. This paper kind of implies that fixing the token noise will make LMs reliable. But what if there is something more fundamental missing?
That's a fair point. It's not a silver bullet, of course. And yes, there are probably limitations inherent to token-based analysis. But even if it's not the full picture, it's still a powerful tool for uncovering unexpected behaviors and biases. Just think about the implications for marketing research, which is something the paper touches on. If you're using an LLM to test consumer preferences, and its responses are being skewed by token noise, you're getting bad data and then making potentially bad decisions from that.
Absolutely. And the paper mentions discrete choice experiments and conjoint analyses. These are all commonly used in marketing. You can easily imagine a scenario where a subtle phrasing change or even adding seemingly irrelevant tokens like the word only could completely throw off the results, and you would never know. The insights gained here are not just theoretical. It's practical stuff that can save a lot of resources and avoid wrong conclusions. This token sensitivity highlights how critical it is to not rely on these models without understanding their mechanics.
Yes, and if you think about it, it's kind of scary that we are already using LLMs in so many different applications, from generating marketing content to helping with legal tasks, without fully grasping what's actually going on inside. This token noise thing isn't just a quirky phenomenon. It's a serious problem that could be leading to inaccurate conclusions or even biased outcomes, and we are blindly trusting them.
And that's why I think interpretability is so crucial. It's not just about making the models more accurate, it's also about making them more transparent so we can actually understand their limitations and potential biases, and importantly, fix them. I also think it's important. What this paper does is to make all of this accessible. It allows researchers to look into closed models, and we can have a more open and democratic discussion about their biases, which is always a good thing.
Right. I mean, the fact that the method doesn't require access to the model's weights is a game changer. That's often the biggest hurdle for research. You're stuck with whatever API access the company provides. With a tool like this, you can do your own analysis and get a better grip on what's driving a particular decision. It's like having your own personal LM debugger.
I'll give you that model agnostic is a big win, no question. But still, I'm not entirely convinced that simply removing token noise is the path to true understanding of the model's reasoning. It's like putting a band-aid on a much deeper issue. What about the fundamental algorithms? Shouldn't we be looking into more structured and interpretable architectures from the get-go, rather than trying to explain black boxes? I still don't get why we are so focused on neural networks when they have such limited interpretability and generalization capabilities.
But that's where neuroscience comes back into the picture. We don't necessarily have to throw away the current paradigm. We should be asking how the brain accomplishes these things with such efficiency and minimal energy usage. We need to be inspired by biology and combine neural networks with other approaches like symbolic AI, or even exploring totally different architectures that more closely mimic the brain's own processing. I think approaches like this, which gives more insight into these black boxes, could help us get there. It helps us understand the fundamental mechanisms of how information flows inside, and that insight should eventually lead to a better architecture.
See, I think the path towards AGI lies in scaling and fine-tuning the current deep learning approach. It might seem messy, and yes, we definitely need better interpretability tools like this Shapley value method, but I don't think we need to abandon what is working. What I believe is that as the models get larger and the data richer, the token noise will diminish. It's like learning a language. You start with the basic words, and as you learn more complicated structures and concepts, you stop being distracted by individual low-level features.
You're talking about emergent behavior, I guess. But emergent behavior is not the same as understanding. That's my point. Just because a model starts to behave more like a human, it doesn't mean it actually comprehends or reasons like a human. It could simply be mimicking statistical patterns it has seen during training. And that's a very different thing. And that's why I believe we need to look for more grounded, symbolic approaches. Or, I don't know, maybe something totally different, something we haven't even thought of yet.
Well, that's the million-dollar question, isn't it? What asterisk is asterisk understanding in the context of AI? And how do we know when a model has it? I think papers like this are crucial because they are forcing us to confront that question head-on. They're pushing us beyond the simplistic input-output paradigm, and they're showing us that we can't just take these models at face value. We have to be critical and inquisitive and build methods to properly analyze what they are actually doing. And that analysis, I feel, should combine the best of computer science and neuroscience, for sure.
Right? And that's the power of this Shapley value approach. It's not giving us a definitive answer, but it's providing us with a critical lens through which we can analyze these models. It's like having a microscope to look at the inner workings of LLMs. Before we were guessing, now we have a tool to start quantifying things. And that's a huge step forward. And even if the token noise diminishes, we still need to make sure that other potential biases are being taken into account. So interpretability is not just about today, it's about the future of AI as well.
Okay, so let's say I'm convinced that this is a useful tool to analyze the models we have right now. Fine. I'm not fully convinced it's the path forward, but it's definitely useful. What other kind of applications could this approach have? Beyond marketing, I mean.
Well, think about any area where you're using LLMs to make decisions or generate recommendations. Take medical diagnosis, for example. You could use this method to understand why an LLM is suggesting a particular treatment. That would not only make it more transparent, but it would give doctors the tools to understand what factors the model is focusing on, so they can either agree with it or disregard it if it's clear it got it wrong. Or even in finance, understanding why an AI is predicting a market downturn would help to identify biases and help to make better investment decisions. It's about building more reliable and trustworthy systems, and that goes beyond marketing.
Yes, and think about legal applications as well. If you're using an LLM to review legal documents or generate legal advice, you would absolutely want to know what specific parts of the text are influencing the model's conclusions. You could use this method to identify potential biases or even errors in reasoning which would be crucial for ensuring fairness and accuracy. It's not just about making the model's output understandable, it's about ensuring accountability and building confidence in these systems so we can rely on them and benefit from their capabilities.
Okay, those are some really good examples, I must say. The medical and legal ones are particularly important, and it goes directly to the point I raised earlier, that we're blindly trusting these models. And I think this method can definitely help to at least reduce some of that blind trust. But I still find it unsettling that something like a word, or a new line, can carry so much weight on the final decision. It means they are not truly processing meaning like we do, right?
Exactly. And that's the point. The paper is not saying these models are intelligent. It's saying that they're really complex statistical systems, which often work differently from human cognition. And we can't assume that, just because they can generate human-like text, they are actually understanding or thinking the way we do. We should keep that in mind when using them. And by analyzing them with methods like this one, we can pinpoint where these divergences occur, which is crucial in understanding what is going on. This tool helps us find the limitations, and that's what good science is all about, knowing where the boundaries are.
Yeah, and the paper emphasizes the need for researchers to report their results conditioned on the specific prompt templates they use. That's really important because, as we've seen, even minor variations in the prompt can lead to drastically different outcomes. So, we need to be extremely specific and transparent about the experimental setup. It's no longer sufficient to say, we asked the model this question. We need to document every detail like a scientist would when they conduct an actual physical experiment. The prompt is just as much a part of the experiment as the model itself.
That's a very good point. And yes, it's obvious if you think about it. If the models are so sensitive to specific tokens and formatting, we need to document every single one of them. That reminds me of the early days of AI, where people were training models and they would break when the training data was slightly different. It's like we've come full circle, and now we are seeing the same limitations even with much more complex models. They are still very sensitive to details.
It's fascinating, isn't it? How far we've come, and yet how much more we have to learn. And I think we should learn from our past mistakes in AI. By acknowledging the limitations of current approaches and by building tools to analyze them, we can make sure that we're building more reliable and responsible AI in the future. And that's what it's all about, in my opinion.
Absolutely. And the fact that this paper is focusing on interpretability and not just on increasing performance is very encouraging. It shows there is a growing awareness in the field that we need to understand the models and not just blindly trust their outputs. I think this is just the first of many interpretability methods that will emerge, and it will become a core part of the development of future models. I'm very excited about what's next because this will allow us to really build useful and trustworthy AI.
Yes, and I think we should take this opportunity to look back at the more grounded approaches to AI. Maybe there is a middle ground. Maybe we can find a way to combine the power of deep learning with the interpretability of symbolic AI. But definitely, methods like these are incredibly important, at the very least, to analyze and make sense of the black boxes that we have right now.
Yeah, and I think the neuroscience angle becomes even more critical at that point. If we're going to build truly intelligent machines, it's not enough to just look at algorithms or data. We need to understand how biological intelligence works at a fundamental level. How does the brain process information? What are the underlying mechanisms that give rise to things like consciousness and understanding? I think this paper and others like it can open up these exciting possibilities.
I agree. I think it's about building that bridge between different disciplines. And I think this paper does a great job of highlighting where we need to focus our attention, what the limitations of the current models are. And with these interpretability methods, we are getting closer to fully unleashing their potential, not in the far future, but in the present.
All right, I'm still not convinced we're on the path to true AGI with the current methods, but you've both made compelling points. And yes, I must concede this Shapley value method seems like a valuable tool. I'm very curious to see how it's applied in different contexts going forward, and hopefully it can point us to the right direction, whatever that may be.
Exactly. And that's what this show is about, right? To explore different perspectives and push our understanding of this complex field. Thank you for joining us this week for this insightful discussion.
Yes, and I think it is important to say that progress is always a collaborative effort, and this discussion is a testimony of that. Thanks everyone for tuning in.
Yes, thanks for this lively discussion. It was very stimulating.